Okay, let's start our fresh topic. Dimensions of physical quantities. So before we come to the formal definition for it, let's discuss some pretexts. So with the help of dimensions, we can determine the nature of a physical quantity. So let's say we have seven fundamental quantities, and these seven fundamental quantities are used to derive all the physical quantities. So we can call them seven dimensions, and then we can represent other physical quantities in terms of these seven fundamental physical quantities. So what do? We use a square bracket to indicate that the quantity represented here is in its form of dimensional formula. So let's take some basic notations for these fundamental quantities, and then we will come to the other physical quantities. So the first one is, we can say, there is nothing like first or second, but yeah, we have to start from somewhere. So mass we represent with capital M enclosed with square bracket. Then we have length, so we are going to represent with capital L, and then we have another basic physical quantity which is time, and to represent this quantity we have to use capital T enclosed with square bracket. Okay, so these three out of seven, there are four more. We know about those quantities. In case you want to know more detailed discussion about this, then you can refer to some previous videos in the same playlist. So four more, they are here: thermodynamic, temperature, and we write capital K. Then we have luminous intensity, we write small c v. Then we have electric current, and we write capital A, derived from ampere. And then we have the last one, the amount of substance, the amount of substance, and we write it as mole. So in mechanics, we are going to use these three fundamental physical quantities mostly to express all other quantities. But we can use these quantities also as and when needed. Okay. So let's take some examples. So let's say we have to represent area. So suppose we are writing what is something, let's say we have to represent area of a square, so it should be side into side. So side into side, here we have measured the length of side. Okay, let's say this is a square and its side are a. So what we write, a into a. So this is length, this is length. If we write what is the dimension of area, so what do we need to do? Suppose we have represented area in this way. So this is dimensional representation of area. And for length, side is nothing but a kind of length here. So for length, we have to write L multiplied with L. And then we have L square, or we write it this way, L square. So this is dimensional formula of area. Now we have one more thing here. We are going to use these three basic quantities here. So if we want to represent area completely here, we can write area it has no dimension in mass. So M0, it has L2 and it has P0. So this way we can represent dimensional. Of course, we can use uh, the remaining basic physical quantities, but we are limiting ourselves to mass, length, and time because most of the quantities in mechanics we can represent with these three things only. Okay. So, okay, what can we say here about dimensions of area? So we can say this area possesses zero dimension in mass, zero dimension in time, and two dimensions in length. In the same way, you can go for volume also. So I'm leaving that part to you. And now let's take another example, velocity. So dimensional formula for velocity should be what it should be. Velocity is displacement over time. So here we have a quantity which has nature of length, and here we have time. So if we are going to write dimensional formula for velocity, it should be length upon time. And how can we write more elegantly? Can be written as L P to the power minus 1 or P inverse. So if we are including mass also here, then we have velocity m0 L P to the power minus 1. That is, velocity possesses zero dimension in mass, one dimension in length, and one dimension in actually inverse time. So this way we can represent any physical quantity in terms of these basic dimensions. So now we are ready to define. We can write a formal definition for dimensions of physical quantities. So what we are doing, we are expressing a physical quantity here in terms of basic physical quantities, and we are raising them to the optimum powers. So what we are doing here, suppose we have to write for area, this has two dimensions in length. So we are doing L to the power 2 and first zero dimension in mass and time. So this way we are representing. So dimensions are nothing but the power form representation of a physical quantity in terms of basic physical quantities. So we have a formal definition here. The dimensions of a physical quantity are the powers to which the base quantities are related to represent that quantity. So you can take it as definition of dimensions of physical quantities. Let's topic is um, dimensional equation. So this is also a easy topic but very powerful. So dimensional formula and dimensional equations. So if you observe carefully, we have already used these things. Now we have to identify them. So what is dimensional formula for a physical quantity? For example, we have written L to the power 2 m0 t to the power 2 for area. So this is dimensional formula for area. And if we are equating that area, let's say we are representing area, okay, writing with full words. Okay, so area we are representing this way. And if we are equating dimensional formula to the physical quantity, this equation we can call dimensional equation for area. So this is dimensional equation for area, and this much only is called dimensional formula for area. Okay. So in this way, you can extend the discussion to other physical quantity also. Let's say if we are representing velocity with this Greek letter epsilon, we call it epsilon. So we can write m0 L to the power 1, but we are not writing, we are looking at just L to the p to the power minus 1. So this is dimensional formula for velocity, and if we are equating this dimensional formula to the physical quantity velocity, this is dimensional equation for velocity. I hope you have got a clear picture about dimensional formula and dimensional equation. Okay, let's continue our discussion. Dimensional analysis and its applications. So one thing, look, quantities can be added or subtracted which have same dimensions. What does it mean? Let's take velocity. So velocity can be added with velocity only. You can't add velocity with time. Suppose you have two different values. Let's say you have given velocity to be 2 meter per second and you have time, suppose 2 seconds. Now, if you want to know what is velocity plus time, so this is not the way we can add them. Actually, we are not going to add them. This is what we already stated here. Quantities can be added or subtracted which have same dimensions, because look, velocity and time has different dimensions. Velocity can be added with velocity, or if you are taking magnitude only, then it can be added to speed also. But let's be, because those velocity or speed both have same magnitudes. The only thing we have to be careful about velocity, that it has direction associated with it. So we have to go for vector addition or subtraction rules. Now, time can be added with time only. You can't add time with velocity. This is what same dimension quantities can be added or subtracted. This is one thing. And we call it principle of homogeneity of dimensions. So the first thing is the principle of homogeneity of dimensions. Okay. Now you can say, okay, this is very easy thing and we already know it. What is its application? How can we apply this concept to get a better or fruitful results? So let's take an example, then it will be little obvious to you. Let's say someone has written displacement formula as ut square plus half at square. And I want to know that whether this is correctly written or not. Okay. Let's say there is a body which is starting from a reference position. Let's say here is equals to 0. And then with initial velocity u, it travels up to time t and reaches here at, let's say, s equals to s. Then the formula for this displacement is given by this thing. Now you have to check whether it is written correctly or not. So how can you check? Look, here we have two terms. One is here, another is here, and this is equal to this displacement has the dimension of length, so it should be this way. Yeah. In the same way, here we have two terms which has been added, or which we are going to add. So these two terms should have the same dimension. Let's check whether it is correctly written or not. This is velocity. It should have dimension of L e to the power minus 1 m0. This is time. So p to the power 2, and then we have 1 by 2, and this is L e to the power minus 2. I'm leaving this thing. You can check it how acceleration is L t to the power minus 2, and it has 0 dimension in M. So I can write M0, and then we have here e to the power 2. Let's solve a little bit more here. So this will be M0 L e to the power here. It will be 1. Here we have power 2, here minus 1. These two will be giving minus 1 plus 2, that is 1. And now here, actually, we need not to worry about this thing while checking dimensional uh, consistency of our equation, because numbers do not have any dimension. So here we are going to get M0 L, and this one e to the power minus 2 and plus 2 will be 0. So what we can see here, this is dimension of length. This is not the dimension of length, means, and this is dimension of length. So this is correct, but this part is not correct. So now you can actually you can say what should it be? Here it should be 0, and it will be possible only when this is P only. That is, you can say that this formula may be correct only when ut plus half at square is written. So this may be correct. I am saying maybe, you will come to know. But if it is incorrect, then we can say it's definitely incorrect. Now, some quantities do not pose any dimension. I already given an example here, 1 by 2, which is a number. So this number has no dimension. So there are some quantities which are dimensionless quantities. You can check the arguments of special functions like log function, like exponential function. It is e to the power something, let's say x. So this argument x should be dimensionless. In the same way, we have logarithmic function. Yes, logarithmic function is here. Exponential function is here. And of course, arguments of trigonometric functions. These are dimensionless quantities. Now, pure numbers do not have dimensions. So pure numbers are also dimensionless. Pure numbers. And there are some physical quantities which are ratio of similar physical quantities. Let's take an example. Mm, Specific gravity, you can take specific gravity, or you say it relative density. Relative density. This quantity is, okay, let's move to the next slide. Continue. So relative density is nothing but density of the material divided by density of water at 4 degrees Celsius, where it has maximum density. So in this way, we can obtain the relative density of a material. Now, what can we say here? Okay, what can we say here? In numerator, we have density, so it should have dimension of density, and in denominator, again, we have a dimension of density. So ultimately, it is going to be dimensionless. Okay, next point. Some physical quantities may have units, but not dimension. Let's take an example for that. Actually, along with these seven basic quantities we have discussed, we have supplementary units also, no? Those supplementary units, let's say plane angle. So we write plane angle in terms of radian. This is a standard way. We can represent in degree also. So, or grade also. There are several ways to represent, but the standard way is to write in radian. So, plane angle, radian. But what is plane angle? Look, if you can recollect this information, if this is theta and the radius is r and this arc length is L, so we have represent theta to be L by r. And this is represented in radian. But our focus will be on dimension, what it should be. Look, the quantity in numerator has dimension of length and the quantity in denominator it has dimension of length. So ultimately this plane angle is a dimensionless quantity because it has unit. In the same way you can justify the solid angle also. There you have dimension of area divided by dimension of area. I am leaving this part to you. You can do it by yourself for solid angle. Okay, let's continue our discussion. After knowing this fact that there are dimensionless quantities also are there and they may be involved in the equation. So I am going to make a comment here that dimensionally incorrect equations are incorrect for sure. But dimensionally correct equations may or may not be correct. Why I am saying this? Let's take an example, then it will be clear. If we are writing kinetic energy in terms of 1 by 2 m v square. Okay. So here this quantity is dimension of 1 by 2 and this has dimension of energy. Okay. What if I'm going to check this equation whether it is dimensionally correct or not? So this is also dimensionally correct, but this equation is not correct at all. So that's why I'm making comment here. Dimensionally incorrect equations are incorrect for sure, but dimensionally correct equations may or may not be correct. Here we are missing this 1 by 2 here. And although this is not present here, this equation is dimensionally correct. That's why we have to keep this statement in mind while doing dimensional check. Okay, let's move to another application. We can deduce simple equations if we know dimensional formula and we know how to use them. For example, we know a force which is represented as mv square by r. If you know, you can write its name in the comment box. So, force mv square by r. Now, we have given that there is a force which is related to mass, velocity, and some radius, some length type quantity. Now we have to establish relation between force and these three quantities. How can we do that? So we can do here. First, we have to know what is the dimensional formula for force. So we can deduce it from a simple equation F equals to ma. M, this is L to the power minus 2. This is dimensional formula for force. So we can write it here. M L e to the power minus 2. And now let's take this M has power A. This V has, let's write outside first. This V has power B only. And this is also length. So we can write L to the power C. Now what we are going to do? We are going to rearrange these things, and then we have n to the power a, L to the power b, and here L to the power c. So we can write L to the power b plus c, and then t to the power minus b. And now we can equate the powers of these dimensions on both sides. So what will we get? A is 1. So we can write simply A is 1 by comparing this one, m to the power a and m to the power 1. So a should be 1. Now here t to the power minus 2 and here t to the power minus b. So comparing these two, minus 2 should be equal to minus b, or you can say b equals to 2. Now coming to this part, b plus c should be equal to here. B plus c should be 1. So b plus c should be 1. How it will be possible? If b is 2 plus c should be 1, so c should be minus 1. Now you have got all these powers a, b, and c. You can put it back here. So how? Let's write here a, b, c. So how can we do that? We can do f equals to m to the power a, that is m to the power 1, v to the power b, which is v to the power 2, and c is nothing but minus 1. So r to the power minus 1. We can write it divided by r, as r to the power minus 1 can be written as 1 by r. So this way we can obtain this formula. But can you obtain in the same way a composite formula like s equals to ut plus half at square? This way, I don't think we are going to obtain this formula with the help of this dimensional analysis. So you can say this is a limitation where if there are mm, more than one term, so we can not obtain all those terms with the help of dimensional formula. But for simple things, we can obtain this. So here I am leaving you with uh, homework. You can obtain. We know one thing: potential energy. I guess you have studied these things. mgh. You know about this. Now you have to reduce this result by just using dimensional analysis. And I'm saying that potential energy is somewhere related to mg, which is acceleration due to gravity. So it should have a dimension of acceleration, and h, it should have dimension of length only. So with this information, you have to deduce this formula, as I have already worked out one for you. This is f equals to mv square. And so let's check if it is coming or not. In case of any doubt, you can uh, ask in the comment box, of course. So this is all for today. And in the next video, we are going to discuss some previous year questions from your NEET exam.